Welcome all to this series of lectures on deep learning. Today's session is on autoencoders. We will be seeing how an autoencoder works, what is the theory behind it, and also some coding in MATLAB. Please remember that most of the material that you are seeing here is sourced from multiple websites and books, links to which you can find in the reference section, and the code also, which is provided in the links below. If you have any suggestions or comments, please feel free to add it in the comment section, and please like and subscribe. So we'll start the autoencoders lectures. There will be 3 of these lectures. We will start initially with the basic autoencoder, and we'll see what is the theory behind it, and then we will go on to more complicated versions of autoencoders, which include sparse autoencoders. Then we will move on to denoising autoencoders and also stacked autoencoders. Please remember, all of the coding has been done exclusively in MATLAB, so no Python here. Okay, so let's get to the theory. Now, what are autoencoders? As you can see in the figure, autoencoders basically convert an input image into its compressed representation. So you have an artificial neural network which converts an input that is given to it into its latent space representation. This is very similar to what you will find in say data compression or in dimensionality reduction. So this is similar to other data compression or other dimensionality reduction techniques that you may have seen, like PCA. But the main difference between, say, principal component analysis or PCA and autoencoder is that the autoencoders are capable of learning a lot more type of interesting patterns that can appear in the data. PCA is not able to do that to a large extent. However, there is the idea of autoencoders being an unsupervised type of machine learning algorithm. There is some dispute on this. The reason why we call autoencoders as unsupervised machine learning algorithms is because there is no specified class labels, as you will see. Whatever is input, the same image is the output as well, or the target as well. So as such, there is no specific class labels which are assigned, and therefore it is usually considered as an unsupervised learning algorithm. However, there is a school of thought which says that because it does not work like a typical unsupervised learning algorithm or machine learning technique, it can be thought of as a self-supervised learning system. So there is a little bit of argument about that, but still the idea is that you do not have to specify a class label to any of the samples that you are giving in, and it basically tries to compress whatever you have given, maybe 1D or a 2D image, and then tries to reconstruct the same image. If you will look at the image that is given below here, you will see that the first layer is the input image, then it compresses the image into its compressed version or latent space representation, and then you have another layer which will actually pull it up to the basic dimension that it had, and then you get the reconstructed image. So that is basically what autoencoders do, and we will now see some of the terminology that is associated with autoencoders. Okay, so now what we are going to see is what are the features of autoencoders. The main features of autoencoders include the fact that they are not general purpose encoders. Well, that is one of the major drawbacks of autoencoders as well. mainly because autoencoders can compress data which they know about. They are not general purpose compressing type of algorithms, and that is what makes them very different from what you usually see as the compression algorithms, MP3, MP4. All these algorithms are capable of compressing data without learning anything about the data. So in that way, they are very different from conventional um, algorithms for compression. Second major feature of autoencoders is that they are lossy compressors, which basically means that the reconstructed image will always be slightly worse than the actual input image that you had given. Or if you're trying to reconstruct an audio sequence, the reconstructed audio will be of slightly poorer quality when compared to the original audio that you had input to the system. Uh, the third major important feature of autoencoders is that they learn automatically from data. You do not have to specify any way of encoding the data, or you do not have to specify what they are supposed to learn. They learn automatically. So that is one major advantage of using this as well. So what you have seen now is the three major aspects of autoencoders. Um, the first two are mostly the disadvantages. As you can see, they perform worse when compared to MP3, MP4 type compression techniques, and they are also kind of poorer in performance when compared to non-loss or loss-free or lossless type arithmetic type compression techniques. So these type of algorithms, that is autoencoders, do very well for data which they have seen before, but for generic applications this cannot be used. So that is the major takeaway that you can have from this particular instruction or slide. Okay, so what are the major applications of autoencoders? You will see that the major applications of autoencoders in real life today are two. First one is to denoise images, and second one is to reduce the dimensionality of the input data. So these are the two applications where you will find them being used practically. For all other applications, they have been superseded by other algorithms which are more efficient and more effective. But still, you will be able to get reasonably good results when you're trying to perform image denoising. You can see here, this is image denoising example. You have a corrupted image on the left hand side and the regenerated image on the right hand side. So you will be able to reconstruct your images to a certain degree. Now we go to the architecture of autoencoders, and as you can see, the architecture of autoencoders includes three sections. First one is the encoder section, second one is the code section, and the third one is called the decoder section. Okay, so the first layer is the encoder layer, code, and decoder. So if you look at this a bit more in detail, you will find that the encoder section compresses the image or the data that has been given to it into a smaller size. So which is basically accomplished by using the hidden layer. Typically what happens is that in autoencoders, the number of neurons in the hidden layer is much lower than the neurons in the input layer, and this basically forces the network to compress the information content in the input so that the hidden layers are able to retain most of the information that has been given to it from the input layer. And as you can see, there is also an output layer which is associated with the autoencoder. So what happens is that once the compressed representation is available, the decoder section tries to reconstruct that input by basically matrix multiplication, and whatever hidden representation has been learned, that is used to translate the hidden layer representation into the output. We will see mathematical representation of how this happens in the next few slides. So you can see here encoder is one, the code section is the compressed output, and then you have the decoder output. The hidden layer is also referred to as the bottleneck. Bottleneck is what actually produces the compressed representation. So as you can see here, the example that we have given has got 6 neurons in the input layer. You have 3 neurons in the hidden layer, and again 6 neurons in the output layer. So whatever input comes in goes into the input layer. It gets compressed into the form that is given by the hidden layer, and then the output layer tries to reconstruct that particular pattern that has been input to it. Okay, so the major parameters which an autoencoder has to deal with before it can work properly are the code size. This is exactly the same as the number of neurons in the hidden layer. If you look at the diagram on the right hand side, you will find that you could have more than one number of hidden layers. All right, so this is an example of what is called as a stacked autoencoder. What we are actually trying to say here is that it is possible that you have more than one hidden layer, and the center part that you see here, the part which has got the lowest number of neurons, is typically referred to as the code size. Say if you have 3 neurons in the hidden layer which has got the smallest number of neurons, then the code size is 3. And please have a look at the figure once again very carefully. You will see that we are reducing the number of neurons successively. There is no sudden increase and then decrease. You will see that it is monotonically decreasing till it reaches the code size, and when reconstruction happens, you are reconstructing back at the same scale. So this is typically the way in which most of the autoencoders are set up. The number of layers we have already discussed. You can have as many number of layers as you need. A number of layers per node is also possible, so you can decide on what number of neurons should be there in each layer. There is no hard and fast rule on how many neurons should be existing on each layer of the hidden part. You can choose your own. And the last thing that you have to be very careful about is the loss function. Typically, the loss function that is used is either cross entropy or the mean squared error. Both of these things we have seen in the previous classes, so it should not be a very difficult thing for you to understand. And now what we are going to see is what are the typical variants of autoencoders. We had a small introduction to what are the different variants. I did give you a small overview of what are the variants of autoencoders at the beginning of this lecture. But more formally, the variants are like this. You have the typical regular autoencoder, which does not have any bells and whistles basically. The second type is what you have is sparse autoencoder. This is slightly more complicated than your conventional autoencoder in the sense that you have added a little bit of complexity to the algorithm by adding a regularization parameter and a sparsity parameter so that the autoencoder does not become over complete. The third category is a stacked autoencoder, in which case you have multiple encoders stacked one on top of the other, and then you have multiple decoders also stacked one on top of the other, and then you have the final output. So these kind of autoencoders, the stacked autoencoders, are capable of learning a lot more complicated patterns than what a typical plain vanilla type autoencoder can learn. The fourth type is the denoising autoencoder. The denoising autoencoder is a very small modification to the regular autoencoder architecture that you will see in the first three cases. In that, it just tries to add one additional layer at the input side. We will see that in the later sessions. And the last one that you will find is the variational autoencoder. This is slightly different from the other four that we have seen so far. Um, we will be seeing variational autoencoders when we go into um, reinforcement learning, and after that we may go to GAN type networks. So there we will try to see variational autoencoders. They're slightly more complex when compared to normal autoencoders of the first four type. So in the forthcoming sessions, we will be only discussing the first four type of autoencoders, and the fifth one we will see later on in the future sessions. So we'll start with first some reminders on what we have seen so far. We have seen that autoencoders are unsupervised. We also discussed why there is a bit of conflict on that part. And we also saw that there has to be a cost function in this particular case as well. Obviously, all type of artificial neural networks work on a cost function basis, so that is important. And what cost function does is the same thing. So it's similar to what you will find if you're trying to do a curve fitting kind of an example. You have the actual input and you have the reconstructed or the predicted output, and the difference between the two is the error, which is supposed to be minimized by the underlying learning algorithm. We have also seen that encoders and decoders are the two major parts of an autoencoder. And what we will do is we will first start with the plain vanilla type autoencoders, and we will assume that there is only one hidden layer there. So let's see that very quickly. Okay, so let's start with how a typical autoencoder works. You can see the figure on the right hand side. You will find that it is typical fully connected neural network that you have already seen in previous classes. And as you can see, the number of neurons in the hidden layer are smaller than either the input or the output. That's why it is sometimes referred to as the bottleneck also. And it is this layer which learns the compressed representation of the input. So here what we have is the terminology that is associated. You typically have the set of weights which connect the input neurons to the hidden layer, and they are being referred to here as the matrix W. Similarly, you have another set of weights which connect the hidden layer to the output layer, and again that is being referred to here as the V matrix. And the output that you are getting here is with the help of the output neurons. And if you look at this, there the number of neurons in the output layer is exactly same as the number of neurons in the input layer, and the output of each output neuron is the reconstructed input. And as you can see, that is why it is represented as x1 cap, which is the reconstruction of x1. Similarly, x2 cap is the reconstruction of x2, and so on till x6 cap being the reconstructed version of x6. And obviously, we also have bias terms which are associated with the neurons, but they are not typically represented directly because we already know that they exist. So there is no representation explicitly in the diagrams. Most of the time, you will not find them being presented in the diagrams that you will see in literature. but you can put that as well. But please remember that all these kind of fully connected networks do have a bias term for each of the neurons. And typically what we use is the activation functions for the input layer is typically a linear activation function, and the output uh, activation function is also linear. The hidden layer activation function typically tends to be sigmoidal. In MATLAB, you will find this being referred to by the term log sig, which is basically the same thing, 1 by 1 plus e to the power minus n, where n is the input. So this is what typically is used. You can have other activation functions also, but please remember that you need to have a activation function which is continuously differentiable. Tan also will do. So you have the input vector, which is represented by uh, the vector x. You can see here the input vector is input here, and you get the corresponding output as x cap. So at the encoding layer, what happens is that the output of the hidden neuron 1, that is given by out of h1, is nothing but the weights corresponding to each input neuron to the hidden neuron. You can see W11 is the weight from neuron 1 to the hidden neuron 1. So input neuron 1 to hidden neuron 1 weight is W11. The weight from input neuron 2 to hidden neuron 1 is W21, and so on. And then you have the bias term also. So this is the summation that you have to put in, and F denotes the activation function. So this is what we are talking about as the sigmoidal activation function, and the resultant value is out H1. Similarly, you have the other two outputs as well. So if you put all of them together, you can represent it using a single function or single representation, which is like this. In our example, since we have only 3 hidden neurons, I can take only 3 values, and out of hi equals to the activation function. Inside that you have the wixi and phi. So you have this input which is coming to the hidden layer. When it passes through the activation function, you generate the output of the hidden neuron. So if you look at this, the output that you get from the 3 hidden neurons can be represented as out h1, out h2, and out h3. This is the encoded vector. So what has happened here is that the 6 dimensional vector has now been reduced to 3 dimensions. So the x vector is now reduced to the h vector, where h is supposed to contain almost all of the information content that was present in the x vector. Similarly, for each of the inputs, you will have this compression happening. So this is basically the idea behind autoencoders. So creating a compressed representation of whatever input was given to you. So once the compressed image or the compressed representation is available, as the reconstruction part, we go back and we try to recreate whatever was input. So you can see here the output of output neuron 1 is the reconstructed version of x1 input, which is basically same as v11. V11 is the weight from hidden layer 1 to output neuron 1, and multiply it with output of hidden neuron 1 to create this input to the output neuron 1. Similarly, you have the inputs coming from the other two also. That is why you have a total of 3 terms plus a bias term, obviously. And this is passed through an activation function to yield the output. Similarly, you have 6 outputs which are generated, and this will be the 6 reconstructed versions of the inputs x1 to x6. When you generalize this, it forms this. As you can see, this is very self-evident on how this is being done, and you can see the outputs also will be there will be 6 outputs, as you can see here. And just as a reminder, the output O indicates that it's in the output layer. Now what has happened is, as a result of doing this, we have got the decoder vector, which is also of the same dimensions as the input. So autoencoders basic property is that the amount of input, or the dimensions of the input, is equal to the dimension of the output. So whatever you give as input, same thing you consider, or under best conditions, that's what you expect as the output. So 6-dimensional input, 6-dimensional output. So if you summarize all of this, um, your aim is to minimize the reconstruction error. Okay, and input is given in terms of x. In the reconstructed vector that you will be getting, it will be in terms of x cap. So the purpose of the learning algorithm which you will be using, it could be any learning algorithm that you may have used. You could use Adam, you could use Levenberg-Marquardt, you could use gradient descent with momentum, you could use SCG, you could use any learning algorithm with this. But the major objective function that you will have to look at is the error, or the difference between the input and the reconstructed output. All right, and typically what you will find is the loss function being used. MSE, or the mean squared error, is the most common function that you will come across, and this will be the objective function that you will come across very quickly. We have already seen how uh, your other types of loss functions work. This is the most simplest one you can find, and this is also quite effective as a loss function. So in case you do not want to use any other complicated loss functions, this will work just fine. All right, and you can use any algorithms from gradient descent to Adam. Any such algorithm can be used for. And I would also recommend going through all these references which are listed here. They are some of the easiest tutorials that I could come across on this particular topic. There's a lot of other literature available which you can go through, but these are the easiest ones to understand. And next, what we are going to do is we are going to see some coding in MATLAB, which will help you understand the concept of autoencoders a bit better.